Let us see an example for discrete random variable sampling, specifically for the multinomial distribution. Consider the multinomial random variable x, which takes possible values omega equals to 1, 2, 3, 4, 5. In other words, there are a total of 5 possible outcomes ranging from 1 to 5. And here's a table that summarizes the probability that each of these possible outcomes occurs. So px of 1 is equal to 0.1, indicating that there's a 10% chance that the random variable x will take value of 1. There's a 20% chance that the random variable will take value of 2, etc. And you can verify that these sum up to 1. From this, we can get the CDF at each of these points. So fx of 1 is 0.1. fx of 2 is the sum of the x equal to 1 and 2, the probabilities. So that's equal to 0.1 plus 0.2, which is equal to 0.3. fx of 3 is the cumulative sum of the probability in the first 3 possible outcomes. So that's equal to 0.6. fx of 4 is equal to 0.1 plus 0.2 plus 0.3 plus 0.2, which is equal to 0.8. And then fx of 5 is equal to 1, which is the sum of all of these. Note that you don't always have to do the cumulative sum yourself. You can use the cum sum function in R, which stands for cumulative sum, instead of summing them up yourself. By plugging in the p vector into the cum sum function, it will give you the corresponding f vector over here. So now let's try to draw 1,000 samples following the 3 steps in the inverse CDF method. In step 1, let's try to make an R function called H multinom, which has the following properties. It takes inputs u and p, where u is a number between 0 and 1, and p is the vector for the probability of each outcome between 1 and m. For our example, we know that m is equal to 5, but of course this is generalizable to other multinomial distributions. This function takes u and p as the inputs and outputs xi if the u value that we supply is right between fx of xi minus 1 and fx of xi. So let's see how the function is defined. The inputs are u and p, and then first we use the p vector, which is the probability of each outcome, to get the f vector, which is the fx, the cumulative sum we showed earlier. And here we use the cum sum function. And we further know that the length of p is equal to the number of outcomes. So we know that we set that equal to m. So that's the number of possible outcomes for the multinomial draw. Now we are going to compute what x should be equal to. Of course, by the earlier procedures, you can write a series of if statements and verify that if u is between each of the intervals, the consecutive fx's. Then, however, there's another way to implement this. So first, we initiate the value of x with the minimum possible outcome, which is equal to 1. We know that the possible outcomes are from 1 all the way to m, so 1 is the smallest it can take. And now we're going to write a for loop inside which we are going to iterate through each of the possible outcomes from 1 through m. So for I in 1 through m, we're going to add 1 to x every time we find out that u is greater than f at xi. So in other words, we're going to increase the value of x by 1 every time it passes another u test. You can verify that if we compute x in this way, the outcome we obtain satisfies this property. And then in the end, we return the x value. Steps 2 and 3 are quite straightforward. In step 2, we draw the random uniform samples using our unit 1000. And in step 3, we perform the transformation. So first of all, we need to supply the p-vector. So at this point, we haven't told R what are the probabilities for each possible outcome. We just feed the probability vector for outcomes 1, 2, 3, 4, 5, and that we have defined in the example into R, and we call that probs. And then the next step will be the transformation. Let's call the new object xmult, denoting the random samples obtained from the multinomial distribution. We obtained this by applying the h-multinom function we defined to the u vector, the uniform 1000, and supplying the probabilities. In the end, we will get a length 1000 vector of the draws that are obtained this way. Let's take a look at the draws we have obtained this way, the xmults, and see whether it looks right. First, let's try to see the relative frequency of each of the possible outcomes inside xmult. This is obtained by doing a table of xmult divided by 1000. And we can see that the outcome 1 occurred about 10% of the times. Outcome 2 occurred about 20% of the times. Outcome 3 occurred about 29% of the times, which is close to the theoretical probability of 0.3. And then outcomes 4 and 5 occurred both 20% of the times approximately. So you can see that it seems like this generator works quite well. The samples we obtain actually also follow the theoretical distribution that we have defined. Instead of doing this from scratch, there is a built-in function inside R called sample, which may be used to draw discrete random variable samples. For example, we can repeat the earlier task using the sample function. Let's create a new vector length 1000 called xsamp, and that's equal to sample x from 1 to 5, so these are the possible outcomes. Size equals 1000, which tells R that we want to draw 1000 random samples. And then prob is equal to the probs vector, which is the probability vector for each possible outcome. In the end, we specify replace equals true, telling R that we want to sample with replacement. And let's look at the relative frequency of the xsamps obtained using the built-in R function. You can see that in this case, it's quite similar to the earlier case, and that the relative frequency that each of the outcome occurs is quite close to our theoretical distribution as well.